Okay, so I am going to ask if there are questions for the homework, but I'm going to ask that in a second. So before that, where am I here? Welcome back, everyone, to our next Calculus A lecture. So we're going to continue discussing right where we left off last time, discussing differentiation. And I'd like to start with the following problem. So the problem is x squared sine x to the power of 20. And the question is, differentiate this. So that picks up right where we left off last time. And the question is, how do I differentiate this, right? So can anyone tell me?
With respect to what variable?
Oh, okay. Single variable calculus class. What do you mean? We will always be differentiating with one variable. The variable is x. But yes, fine, acceptable question with respect to x. So how do I differentiate this?
Start with the power rule. So you'd have 20 times x squared sine x times,
What is the power rule? Can you give me the statement of the power rule?
if you have a function raised to a power, the derivative of that function is the power times the function raised to raised to the power minus 1 times the derivative of the function.
Okay, but that's a special case of another rule. What's the more general rule?
I have no idea.
Oh, okay. Well, chain rule, right?
Sure.
So what does chain rule say? Chain rule says, suppose that you have a composition f composed with g of x, and you want to differentiate this. Then the way that you differentiate this is, first off, you have to find the derivative of the outer function f, and then you just plug in g of x. Where's my cursor? Why is it doing that? Here. And then you multiply by the derivative of g prime of x, right? So if we look at this function right here, what we have is let's say that f of x is equal to x to the 20th power. So this is the function that takes some value and multiplies it with itself 20 times, or raises it to the 20th power. And then we have the function g of x. And let's say that that function is x squared sine x. Right? So the function that we have above is f of g of x. That's x squared sine x raised to the 20th power. You've taken the x inside f of x, and what you've done is you've substituted in place of that g of x, which is x squared sine x, right? So that's this function. And then how do we differentiate it? Well, we think about each one of these problems. What does chain rule really say? Chain rule says that if I want to differentiate a composition, if I consider that a problem that I have posed to me, then I can do it. I can solve that problem provided that I can differentiate f and I can differentiate g, right? This is how you put them together after you've differentiated them, right? So let's try and do that then. What's the derivative of f? F prime of x. What's that?
(20 times x to the power 19).
Yeah. And then we try and differentiate g. And what do we get? What happens? What do we use to differentiate g?
Rule.
And what's the statement of product rule? So let's say I have a function f of x and a function g of x, and I consider the function given by their product and I differentiate it. What's the derivative of that?
You would find it's f prime of x times g of x plus f of x times g prime of x.
Yes. Right. Okay. So, I mean, calculus has nothing to do with this class if I'm breaking the fourth wall here. So you probably know calculus. If you don't worry about it. But also think about these rules syntactically. Okay, not breaking the fourth wall anymore. We're back to our calculus A class. Right. So if I want to do product rule, I look at this function, x squared sine x, and you're saying that it's a product, really? Is it a product? What is it a product of?
It is a product of what we can consider to be two functions. One function is x squared, the other function can be sine of x. They take x as the argument.
Good. So we say, look at g of x. I want to differentiate it. Well, I've recognized, I've actually done this, that g of x is a product of two functions. The first is x goes to x squared. The next is x goes to sine of x. Now, how do I differentiate a product then?
We differentiate it according to the product rule, which we just outlined.
So what do I get?
Oh, you get 2x times sine of x plus x squared times cosine of x.
Good. Now, I actually want to compute the solve the original problem. So if I have f of g of x, and I want to differentiate that, what do I actually get?
You take f prime of x and you replace the x, which is under x and 19th, and you replace that x with g prime with g
No,
of x.
not exactly. G of x, right? And
then
that's
you multiply
x.
by, yeah.
And then I multiply by what?
By g prime of x.
Yes. And that's how I differentiate the function. So in other words, what were the key steps in order to doing this derivative? There were two things. First off, when we just looked at this function, we had to choose which rules we were going to apply, right? And how did we choose which rules we were going to apply? Well, we looked at the function and we said, you know what, this function, I can view it as a composition. I can view it as a composition where the outer function is x goes to x to the 20th, and the inner function is x goes to x squared sine x. And then in turn, after we've recognized that it's a composition of those two functions, we say, you say, I'm going to apply chain rule. Then once you've made that choice, once you've made the choice that you're going to apply chain rule upon having recognized the function as that sort of composition of f and g, everything else that you do, your hands are tied. Now that you have f and g, you know, chain rule says that your problem becomes differentiating f and differentiating g. Nothing else in the world matters. There is nothing in the world except for the problem of differentiating f first and then differentiating g. You can forget about everything you were doing before. It's just solving that problem. Then, after you myopically do that, you go back to the end, and now that you have the derivatives, you put them together like this. Now, in our myopic perception, when we were doing this, we had to differentiate g prime of x. And then g prime of x, we said, we had to differentiate g of x. How do we differentiate g of x? Well, you look at it. How do you differentiate this? Then you have to make the right choice. You have to recognize that g of x is a product. And you have to recognize that it's a product in this way. Now, once you've made that choice, that you're going to apply product rule by decomposing g of x as a product like this, your hands are tied again. Now the problem just becomes differentiating the first factor and differentiating the second factor. Nothing else in the world matters. It's only differentiating those. And once you finish that goal, you go back and you put them together. And then you've differentiated g prime. And then you go back. Now you were differentiating g prime for the sake of applying chain rule. And now that you have differentiated both f and g, you put them together in this way. And that gives you the answer. So, okay, breaking out of this calculus A illusion, what we've just done here basically describes math and proof writing as well. There are two elements to math and proof writing. The first is knowing which rules you have at your disposal and how those rules work. In this case, your two rules, your two big rules, I guess, are chain rule and product rule. And you need to know that, for example, in order to apply chain rule, you need to have a composition, and you need to explain how it is that your function is a composition. And then you need to know that if you recognize a function as a composition and apply chain rule, that what you have to do in order to apply chain rule is differentiate f, differentiate g, and then afterwards put them together in this way, right? Does that make sense?
Yeah.
And similarly, product rule, it's similar. If you have something that you recognize as a product, well, you first have to recognize it as a product. You have to explain how you've recognized it as a product. And then you say, I'm applying product rule. Then after you do that, your hands are tied. Your goals become necessarily to differentiate the first factor, to differentiate the second factor, and then put them together as it says here. So that's the first aspect of math, knowing what the rules are and knowing how to properly use the rules. The second aspect of math is knowing which rule to apply. I mean, if you have, for example, a product of three things, there are different ways to write it as a product. Even this function that looks like a composition, you can write it as a product of the function 1 in a fairly trivial way. So the fact that you had to apply one of these two rules, well, it didn't require as much creativity for differentiation, but when you do integration, there's a lot more creativity involved. And so what we learned from this is that really there are two things to playing in a system. Here we're playing with the system of calculus A functions and rules about differentiation. So I'm going to write it like this. In the system, of calc A functions, and differentiation, as with all systems, I'll highlight that just to emphasize. The game involves two aspects. One, knowing its rules. And two, knowing what plays to make. Similarly with chess. Chess has two levels, knowing the rules of chess, knowing how pieces move, knowing how to capture pieces, etc. And two, knowing actually which choices you should make at every single move in a chess game. And so, of course, the reason that I'm saying this is I'm going to connect this to the homework assignments and how to write proofs. I'm going to more explicitly explain proof writing. So first off, let me say this. I've looked at the homework submissions, and also I spoke to a lot of people on the weekend, and I'm really happy with the amount of effort that people put into those assignments. So I'm given the impression that people really put a bunch of work in. Now, for the people who I spoke with, actually, okay, if you really like this lesson and then you one day go on to teach a course and you think, you know what, I should do it the way Taras did it. And you think about the decision. Well, the decision that I made is that I want everyone to submit a correct argument and that I'm going to individually chase down people and have them resubmit arguments and explain it to them. And that might be effective, but that will make you regret all of the choices in your life that led up to that point. So individually speaking with everyone in the class is incredibly time consuming. And chasing people down for work for having everyone submit correct homework is also very time consuming. But I'm doing it for this problem, but not for any other problem. Okay, that apart. For the people who I spoke with on the weekends, I was convinced that at the end of the conversation, people knew what was going on, but that took a bit of work. Like the conversations were an hour and a half on average. And so I think almost everyone submitted work, but some people still have a bit of correction to do. For the people who I spoke with, I also corrected a lot of their work. For the people who I haven't spoke with, well, I haven't spoken to you yet. So the same process the other people went through, we also need to go through. But to that end, I'm basically going to start by talking about part of the solution to homework 1 and some ideas about proofwriting, with the goal that I want everyone who has an incorrect argument to rewrite their submission and to give me a good proof. Any questions about that?
I think that's great.
Yeah. Let me just see.
So,
this.
do we rewrite the whole proof or just the part that has the incorrect argument?
So if your argument is almost entirely correct, I'll accept it. Like if there are small deviations from the form in which I've asked you to write it, then that's minor. But if after what I explained today, you realize that you need to correct your arguments, then you should rewrite it and just resubmit another argument. I can individually contact you by email and tell you if your argument is wrong. But also, you should also be able to determine it yourself based on what we discussed today. Any other questions? Okay, so now I'm actually going to explain the proof rules more explicitly. And the way that we're going to think about the proof rules is exactly in the way that I described it above. There are two aspects to writing proofs. The first is knowing what the proof rules are. And if you choose to apply a proof rule, how does the goal change? In a sense, there's a creative element involved in choosing which rule to use. But once you've made the choice to use a certain rule, in the immediate future, your hands are tied. And what you're doing is purely deterministic. And then it goes back to another place where you might have a choice to make. So the first thing we have to get down is that you know what the proof rules are and you know how to apply them correctly. And so I'm going to look at the two examples that I had in the notes again. The first example was this proof by the anonymous method. And that claim was for all nuts n, that it was basically n plus 2 is n plus 2, s of n, plus n s of z. is equal to S of S of n. So first off, if we look at this statement, it is a for all statement. If you look at the n that's occurring in here, the only meaning that that n has is in that it is bound to this for all. And this for all is called a quantifier. It is quantifying the logical statement over the variable n. Now, if we look at, for example, the anonymous method, the anonymous method is a technique for proving for all statements. So here, in the motivating example for the anonymous method, we said, well, if n was any nats, then if you just looked at the starting expression, you could start to compute. You'd move an s out, you move another s out, and then you'd have plus nz, and then you just apply the plus z rule, and then you'd have s of s of n. So we could do this calculation without knowing anything about n. And as a result, the anonymous method is appropriate. So you're explicitly making the choice that I am going to prove this for all statement by the anonymous method. Now, once you've made that choice, and once you've also chosen what variable to make anonymous, and in this case, your hands are tied for the immediate future. You write. Go ahead.
Question, just on semantics, what do you mean by anonymous? What does that mean?
So that is the
Why do we
name
say-
for this proof technique. The reason that it's an appropriate name is that we're letting n be any number, but we don't know anything about n. So n is anonymous, essentially. Well, I mean, actually, it's exactly the opposite of anonymous. It has a name, but it has no deeper meaning apart from a name. So maybe that is one thing. But it's anonymous in its identity as a nat. You don't know anything about its structure as a nat. Its structure is anonymous. So in one sense, it's an appropriate name. In another sense, it's the least appropriate name because the only thing that you know is a name. But we're going with that. So, but you should also think of, just formally, as the anonymous method as some proof technique. Now, how do you apply that proof technique? You write, by the anonymous method. On n. Then you say, let's n be any nats. And then every single time you apply any proof technique, you should start the next thing inside with a two proof statement. And the reason that I have you write to prove repeatedly is because the statement which you are trying to prove actually changes. At the start, the statement was for all nats something, right? The only meaning of n was in its binding to the for all. If you remove this for all and replaced it with nothing, then that would be meaningless because n wouldn't have anything that says what it is. N would just be a random symbol. In the statement, n is not a random symbol because it is bound to a quantifier. But if we want to prove a statement for a quantifier, we need to get rid of the quantifier in some way. And n is then bound to the statement, let n be any nat. We're imagining that n is any nat. It could be any nat. It could be z. It could be s of z. But we've stripped away the quantifier. And now what we're proving in a context where n is meaningful with respect to a meaning that is given on the outside, we now have just the statement plus n s of z is equal to s of n. So what we see is that using the anonymous method changed from this statement that had a for all quantifier to this statement that did not have a for all quantifier. That was what this rule gave us. It's a rule that lets you strip away a for all quantifier. In other words, you can only apply the anonymous method or structural induction when you have a for all statement, and it'll change the form of the statement. The anonymous method will change it by stripping away the quantifier, and structural induction will change it by transforming it into two different statements that you need to prove. But anyway, now that you have a situation in which n makes sense and is not anonymous and is some not, you're allowed to calculate. So then you go, we compute. And then can anyone tell me the steps of this computation?
We apply the S rule first.
Yep.
Take one out of the second argument. That's S plus N S of Z, S of Z. Then apply
And the justification was?
plus S rule.
Good. Next.
Next, we apply plus S again. Taking another S out of the second argument of the class. So S of plus N of N and Z. Yeah.
And the justification is?
Plus S.
You're missing something.
S con plus S.
Yes. Because we're working under the S, so the rule that directs the computation under the S is SCONG, and you have to do that. We're actually going to explain why there's multiple SCONGs today in the next thing that we discuss. Anyway, and finally?
Finally, we use two S-cons and plus Z. Yeah.
Yes.
That's S of Z.
N.
N, that's right.
And now look at what we've computed. Our computation shows that plus n S of Z is S of S of n. Now, we end the computation and we look at what we had above. It was this to prove. Have we proven it? We have, right? So we close off at this level of indentation the to prove statement with an as required. Now, what was the, yep.
Why are there two SCONG rules applied? I don't see that part.
Right. So SCONG says that if you have S of something and some rule applies to the thing on the inside, then you can justify transforming the thing on the inside by a rule and then just keeping the S outside. So let's say you've chosen to do SCONG. What is on the inside, right? What is on the inside? This is on the inside, right? So what does that go to in one step? That's a question to you.
Oh, okay. The S of n?
Yes. Now, why does it go from there to there? What's the justification?
I have a plus Z rule.
But the plus Z rule, you still have an S on the outside, right?
Yes.
So what's the full justification?
Then I have an SCONG.
Yes. And then plus Z, right? So if we look at the outer level of S and the thing on the inside goes from here to here. What is the justification? The justification is the green thing underlined here, right?
Okay.
And now that justifies the inside, in order to justify having it with an S outside, you have to do another application of SCONG.
Okay, got it.
Now, so this as required closed off this to prove statement. And what was the next thing that we had on the outside? It was an application of the anonymous method, right? So we let n be any nats, and we proved this statement. So what does the anonymous method let us conclude? The anonymous method lets us conclude that if we let n be any nats and then prove the statement that we want to prove involving n, then we can conclude that for all nats n. The statement that we want. And then I put a very satisfying symbol at the end. This is the most satisfying part about doing a proof, to indicate that you're done, right? So in this argument, really, there was one level of structure. We started with every single time we apply some proof method, the statement that we're trying to prove is written immediately above it. So in the case of just the proof, the statement that you're trying to prove is still written immediately above it in the claim, right? So you can imagine that the claim is sort of a global to prove. Then how do you prove that claim? It has a for all. Well, you need to deal with this complicated structure, and you deal with it by the anonymous method. And that changes the statement that you're trying to prove from a statement that has a for all to a statement without a for all. So this is knowing the rules of the game. The anonymous methods goes from that for all statements to the statement without a for all. And every single time that the statement changes, I want you to write to prove, to indicate what the new statement that you're working with is. And when you apply the anonymous method, just as in calculus, you forget everything on the outside. The only thing that matters in the universe now is proving that statement after the to prove. The things on the outside might give you some rules, and some things like the assurance that n makes sense as a nat. But apart from those assurances, really the only thing that you care about is proving that statement. That's the only thing in the universe that matters. And so you do it. And then when you do it, you can go back and start worrying about what you were worrying about before. Any questions about that proof?
Just one question. The hence stuff, right?
Yes.
I'm like, what? I don't know why this confuses me, but I don't understand why we need to write hence for all nats n and do that thing again. And I don't really understand the anonymous method thing either. There's why can't we just say let n be any nat? Why do we have to say by the anonymous method?
Oh, so, well, I mean, I've done, my template for it has two things. An application of the anonymous method involves both of those things. I could have chosen to have one line that does it, but it is some explicit signaling that you're using the anonymous method, right? So whether it's 2 lines or 1 line is something that I arbitrarily decided. But the fact that you're explicitly signaling it, do you understand that that's important?
I don't think I understand why.
Okay, why? Here's the explanation why. Look at this statement right here in the claim, right? Look at the statement in the to prove. Those are different logical statements.
Yes.
Now, what let you go from one logical statement to another logical statement?
Oh, I see. So you use it to open the quantifier.
Yes. And so this is an explicit proof construction that lets you open the quantifier. It lets you get rid of this
Okay.
technical complication. That's why you keep writing to prove. Every single time you write to prove, it's to signal that you're now proving something different from what you were proving before.
Okay, so just to so if the claim were for some nat n, how would you start the proof then?
Well, we're not talking about that yet. We're not talking about how to prove for some statements. We're talking only about for all. But so this is the for all introduction rule. There is an existential introduction rule as well.
Okay.
Any other questions? Okay, but you did ask a good question with respect to like, why is there an anonymous method? There is an anonymous method because those two logical statements are different logical statements. And it is an explicit proof construction that lets you go from proving one statement to changing your goal to proving that statement. It's the same thing as with differentiation. You have to do two things. So here you recognize that this was a composition, right? Similarly, in the proof world, you recognize that the statement that you are trying to prove. So here the problem is to differentiate a function. In proof world, the problem is to prove a statement. Now, here you recognize that you have a composition. In proof world, you recognize that you have a for all statement. Then you parsed its form. You recognize that it was a composition like this. Similarly, in proof world, you identified what the quantifier was, what the variable in the quantifier was, and what the statement following it is. Then your hands are tied. You just write some procedural things about what the next few things that you're supposed to do is. Now you know that you need to differentiate this and you need to differentiate this. Now, my proof notation involves some signaling that those are the things that you're doing. And then once you write down that those are now your goals, then, okay, your hands are no longer tied. Now you have some creative control again. Now, the problems in your court, the only thing that matters in the universe is differentiating the function f. You can forget about everything else that happened before. It's purely myopic. That's the only thing that matters. So the connection to prove if is your goal is to prove a for all statement. That's the only thing that matters. You recognize that your claim is a for all claim, and you say, I'm going to apply a proof rule. That to write these two lines, no matter what, and then your next statement is a to prove statement. Now, what follows the to prove? The thing here is entirely determined. Your hands are tied. You have no choice. It's what follows the quantifier. Zero choice on the matter. Now, once you've written that down and you indent again, okay, now the ball's in your court again. Now you have some control. Now, the only thing that matters in the universe is proving that statement. How do you prove it? Well, that's up to you. Was this connection between calculus and this helpful to anyone?
Yes.
So calculus is not relevant to this course, but when I teach calculus A students, this is the lesson that I'm trying to get across, that there are two parts to it: recognizing the structure and knowing how the rule works, and then choosing which rule to use. And in every single formal system, in calculus, in proving, in playing chess, there are always two aspects to it: knowing the rules and knowing which plays to make. Okay, finally, I'll just go over the non-anonymous method a bit. Sorry, structural induction a bit. So the proof rule for structural induction, basically this is written in a high level. It says that we can prove a statement. We can prove for all knots n, some statement involving n, p of n, let's say, provided that we can prove the following two statements. So remember, if I write P of Z or P of S of Z, that refers to some logical statements. So what are the two statements that you need to prove? The first one is P of Z, which I call case Z. And the second statement is also a for all statement. It is for all knots K. By the way, the choice of the letter K is completely arbitrary. You can choose any letter, and you should choose a variable that doesn't conflict with the other variables that you currently have in play. So the statement P of K implies P of S of K. So invoking the rule of structural induction, the first thing that you have to do is you have to recognize that your sentence that you're trying to prove, or your original goal, is for all knots n, P of n. Now, once you've recognized it, once you've parsed it like that, and you say, we're doing a proof by structural induction, then your hands are tied. You have to write some standard things, and then you have two goals. You have to prove two different statements. And then when you write to prove, your hands are also tied. What you write there is completely determined. Now, typically, you might want to expand P of Z if you've defined P to be something. So I guess you have a choice of whether you use an abbreviated notation or not. But ignoring that, your hands are tied. The logical statement that you write for the first one is P of Z. No choice there. The logical statement that you write for the second one is for all knots K, P of K implies P of S of K. No choice there. And then your goal now, the only thing that matters in the universe is proving those two statements separately. Now, why does structural induction holds? It's similar to induction in mathematics. Let's imagine that you have a stack of dominoes. This is Z. This is S of Z. This is, okay. And it's an infinite line. And what these two statements say are that you're allowed to knock over the first domino. And the second statement says that if you knock over any domino, then the domino after it falls. And then if you know that's knocking over the first, you're allowed to knock over the first domino, and you know that knocking any domino knocks the next one over, then you can knock down all of the dominoes, right? Now, so again, how do we go in this world where your hands are tied and you're doing an argument? So the claim that I had in the notes was claim for all knots n that plus Zn equals n, right? And then if we wanted to write a proof for this, we discovered that the anonymous method wasn't powerful enough, and that we'd like to prove it by structural induction. Now, by the way, I haven't told you what this statement is yet, an implication in today, but I'll show you how to prove an implication in the course of this proof. Any questions about structural induction? Just the statements of the proof rule. Okay. How long is this taking? Okay. We are going to take a break after I continue discussing proofs, and then we're going to move on to new material. So the proof, you make the decision that you're going to prove this for all statement by structural induction. On n. Now, so the next line is optional. I'd like to make my life easier by introducing a piece of notation. So I'm just going to write if, let's say, if L is any knots, let's P of L denote the statements so this is the same line, plus ZL equals to L. The reason that I've chosen to write L is to indicate that there's no connection between this L and that N. It's just for any knots, I have this statement. This statement, by the way, it is a statement. It is not an expression. It is not some specific knot. It is the logical statement that plus ZL equals L. Okay, and now I have two things that I need to do. I need to do case Z, which is the first statement that I need to prove in proving structural induction.
Question?
Yep.
Why here are we not introducing L by the anonymous method?
So right now, this here, this isn't a proof technique. This is just a piece of notation. I'm just defining, I'm saying that P of L is meaningful. Notice that the L is sort of bound here. What I'm saying is if L, so for example, if I write P of Z, that means plus Z equals Z. I'm not using a proof technique. I'm just introducing what words mean. I'm not transforming the statement at all.
Okay.
Does that make sense? So I could have chosen not to write this line at all, but it would be a bit annoying. So case Z, what am I supposed to prove? This is one statement. So I'm supposed to prove what follows for Z, specifically P of Z, but I'll write this in full as plus Z equals Z. So what happened here is that I looked at the N in the original statement, and I've substituted that with Z, right? So how do I prove that? Well, this one isn't too hard. I write to compute. And then what's the computation? What do I do next? Anyone?
Plus Z. You get Z.
By what rule?
Plus Z.
Yep. So that finishes the computation, and then I close off the to prove with an as required. Now, to use structural induction, I need to prove two statements. I need to prove the statement P of Z, and I need to prove this statement. For all nats K, P of K implies P of S of K. So then I write, and the second statement I just call in the notation for structural induction introduced in the notes, case S of nats. So that's just a name that I have for the following goal. For all nats K, P of K implies P of S of K. And this is why it was good to introduce the notation of P, because otherwise I'd write some equality implies another equality. So remember before when we were discussing the anonymous method, we said that the anonymous methods transformed your top goal, which had a quantifier, into this new goal that did not have a quantifier. Similarly, structural induction transforms your statements. You started off with a claim that looked like this for all nats n plus zn equals n. And now by doing structural induction, it's been transformed into two different claims, which are distinct from the original claim, this claim and that claim. And I explicitly signaled with two proof statements that those two claims are what need proving. Now, that's a for all statement, right? How can I prove a for all statement? So the only thing that matters in the universe right now is proving this statement. We can
The
forget about
anonymous
everything else. Yeah. So there's still a for all. So you say by the anonymous method on what? On what?
K?
Yep. Then you say let K be any nats. And now you're trying to prove something, to prove. So once you decided to say that you're going to use the anonymous method, your hands are tied. These lines are completely determined. Okay, what are we supposed to prove now? Anyone?
It's to prove that P of K implies P of S of K.
Yes. Okay, now here's the part where I need to tell you how to prove an implication, right? How do you prove an implication? And so that's another proof technique. And I called that proof technique hypothetical reasoning. If you want to prove that A implies B, you suppose A and then you prove B. But you're allowed to use A as an assumption when proving B. So you can give it a name. So you write, we suppose, and then we suppose P of K. But I'm not going to write P of K. I'm going to expand what the assumption means, because P of K is just shorthand notation for something. What is it shorthand for?
Plus ZK
Z.
equals K.
Yeah.
Yes. And now I'm going to give it a name, and the name I'm going to choose is int hype for inductive hypothesis. Now, since I suppose that, I'm now supposed to prove something else, and the statement changes. What am I trying to prove now?
Plus Z S of K equals S of K.
Yes. So that's our goal. That's the only thing that matters in the universe. We can forget everything on the outside except for the fact that we have int hype, but we can forget about everything else that we were previously doing. And then we say we compute. And then what do we do? So we start off with plus Z S of K. And now what?
It equals S of plus ZK by plus S.
Mm-hmm. Then
We know from int hype that becomes SK by virtue of
Yep.
SCon and int hype.
Oh, so here's the thing.
Oh, no.
When you're applying inductive hypotheses, it's a
Yeah,
more
there are multiples.
complicated statement than just a single inference rule. It's more honest to not write int hype. Sorry, not write scong.
Oh yeah, you said in Piazza that requires like multiple
Yes.
steps. Oh, okay.
It's more honest to write this than the other way around. At the end of the course, you'll agree. Oh, but we're done now, right? That's what we wanted, right? That's what we wanted to prove. We've computed it, right?
Are we
Now,
not
what do we do
missing an-
now? Go ahead.
Oh, are we not missing an SCON in the second statement of we compute? don't
Right.
need an
So
SCON?
you are not applying a proof rule that looks like this. I wrote on Piazza that it's more honest to not have an SCON here. You're using a complicated inductive hypothesis, which might have multiple steps.
Oh, I meant the line before that.
Oh, but look at here. There's no S on the outside.
Oh, yes, I see it now.
Yeah. So, okay, so we got what we wanted in a computation. Now, did we prove it? Did we prove what we wanted to prove? Yes? Anyone?
Yes.
Okay, so we close off the to prove with an as required. Now, what was above it? We supposed something, right? So what does hypothetical reasoning let you do? Hypothetical reasoning says if you suppose A and you prove B, then that proof technique, that's sufficient for proving A implies B. So the result of hypothetical reasoning is that we can conclude, hence what?
For all nats K,
Nope.
PK, and
That there is no for, so we
Uh,
were, we supposed this, we concluded this. What does hypothetical reasoning give?
Hence, plus the S of K is equal to S of K.
No, that's what we proved here.
Yeah.
Okay, so this line here, this is called P of K and this is called P of S of K, by the way.
Oh yeah. Yeah.
So I'll just write that that is P of K. We supposed P of K. And we proved P of S of K. So if we suppose P of K and we proved S of K, what have we proven?
P of K implies P S of K.
Yes. So this is the proof rule for proving implications. In the same way that the anonymous method and structural induction were things that let you prove for all statements, hypothetical reasoning, which is signaled by we suppose, that's the signal for hypothetical reasoning, is a proof rule for proving implications. When you invoke a we suppose statement, it changes the statement that you're trying to prove from an implication to just being the right-hand side of the implication. Does that make sense? And as a device for proving implications, when we apply the device correctly, when we apply the rule, then we get to prove the implication. Any questions? Okay, what do we do next? What do we close off next?
Hence, for all
No,
mass K
there. What's above it? What was above the we suppose?
is all the way above. It's what we are trying to prove.
Immediately above.
Immediately above.
Above the line we suppose. What did we have?
To prove P of K implies
Right.
PS.
So have we proven it?
We have.
So how do we close off a two proof block? We write as required.
Okay.
So that closes off the two proof block. Then what was above it? Above it, we had the anonymous method, right?
Yeah.
So now, like what you were saying before, now we're closing off the anonymous method. So we can conclude, what was the anonymous method? We wanted to prove the statements for all nats K, P of K implies P of S of K. We said we were doing this, which means we let K be any nats, we proved the statements where K was any nats, and so overall, the boon that grants us is letting us prove what statements?
For all NAS K.
Yep.
Yeah, and the statement P of K implies S of K. No. It's the yeah. P of K implies P S.
Mm-hmm. Okay, and what was above the anonymous method line? It was a what? A two proof, right?
Yes.
So how do we close off that final two proof?
As required.
Yep. So what that handles is, at the very top level, we were going to do this argument here by structural induction. Structural induction transformed our original statement for all nats n plus zn equals n into two different statements. The first statement I called case z. I've written it here. and under this to prove. And the second statement was this for all nats k with an implication. Then, how did I prove that? Well, it was a for all, so I handled it with the anonymous method. That stripped the outer quantifier. Now I have an implication. How do I prove an implication? I use hypothetical reasoning. I suppose the first thing. That transforms the statement into just the second thing, but I have an assumption, which I named. I did it. So that's hypothetical reasoning. I exit. I get the implication. I've successfully applied hypothetical reasoning. I've successfully proved what I said I was going to prove above. Then, what was I doing before that? I was doing the anonymous method. So the anonymous method says that if I want to prove a for all statement, I let k be any nat, and then I prove the thing. Did I do that? I did. So what do I get from the anonymous method? I can conclude a for all statement. Was that the for all statement that I was supposed to prove? Yes, it was, as required. And now finally, globally, we were doing an argument by structural induction. Structural induction required us to prove two statements. Did we prove both of those statements? Yes. So globally, we can close off the bistructural induction block by writing hence. Hence what?
For all nats n plus z n is equal to n.
And that was our original goal. So now we vary with the greatest satisfaction ever, mash that QED symbol. That's satisfying. So, okay, I regret not explaining proof at this level. I left this all in the notes. But now you see how every single one of these proof techniques that we're applying, and all of you, I think basically everyone put in a lot of work into this assignment. So I'm really happy that you did put in the work. So now that you have put in the work, this discussion right now about this should be a lot more meaningful. So hopefully all of you now see how structural induction, how the anonymous method, and how hypothetical reasoning are actual explicit proof tools in exactly the same way that chain rule and product rule are tools for differentiating. Structural induction, the anonymous method, hypothetical reasoning are tools for proving. And in order to apply the tools, you need to prove something else. Or sometimes, in the case of structural induction, you need to prove two different things. But if you can't prove those two different things, then you can use the tool, and that lets you conclude the statement by structural induction. So final remark about proving. The statements that we have in the notes. Sorry, in the homework. So I'm going to discuss PF1 a bit. I'm not going to spoil everything, but I do want the people who haven't submitted it yet to finish, to correct their answers. Or no, almost everyone has submitted. I think only 2 people haven't. But if you know that your answer is wrong, then start to correct it. I want my pound of flesh. I want correct answers from everyone. Okay, so let's do a bit of discussion about PF1. So the statement that we wanted to prove was claim. It was commutativity for all nats. Now I'm going to write the statement like this. I'm not going to write N and M. I'm going to write it with 2 quantifiers. I mentioned several times that these 2 statements are equivalent. Now, this statement, it's a for all statement, but the statement on the inside is also a for all statement. That means that you're going to have to deal with each of these quantifiers separately. Now, I'm going to give you a hint. The way to do it is to deal with the first quantifier by the anonymous method and to deal with the second quantifier by structural induction.
Induction.
Sorry, say that again.
Oh, crap, my mic was on.
Ah, right. Okay. Proof. So let's just do this in the same way that we were doing before. For the first quantifier, we want to handle it with the anonymous method. Now we say let's on n. Let n be any nats. And now we need to prove something. What do we need to prove? Anyone?
Do you have to just say for all nats m now?
Yes. But what? For all nats m what?
Plus nm equals plus mn?
Yes. Oh, there's a comma for some reason above. Yeah, let me erase that comma there. Okay, now that's a for all statement as well. How do we prove that? Well, this statement we prove by structural induction. Now I'm going to give the statement a name just for ease. And I'm going to use the letter L again just to indicate that there's no connection. I'm writing this quickly. Statements, okay, on a new line, I'm going to write it. This is the same line, but page limitations. Plus, so N, do I keep N or do I put L? What is P of L in this case? What should I define P of L to be?
If it's under 4 on SM, then it could be plus NL
Yes, good.
equals plus, should I say LN?
Yes. So
Which
it's
would be
very
N.
important that N is already some fixed nat. N is like some specific thing. We don't know what it is, but it might be Z, it might be S of Z, but it is some specific thing. It's M that's meaningless. It's M that's floating around, right? And so really it's M that we have changing here, the position of M that's changing here. So that's why the N stays put and the M gets replaced with L. Now, structural induction says that we have to prove two statements. So we have a case Z. I'm not going to write what the proofs are. I'm just going to write what the statements are. Case S nat. So in the case of Z, what is the statement to prove? What do you do? What are you supposed to prove?
It's to prove that plus NZ equals plus ZN.
Yes, good. And then you do it as required. Now, what about case S now? What is the statement that we're supposed to prove?
That P of L implies P of S of L.
What is L?
L is any nat.
But so what's the
So
statement?
for all nats, L.
Yeah.
P of L implies P of S of L.
And L is completely arbitrary. We could have called it K as well. But sure, let's call it L. But this L has no connection to that L above. Right. Now, of course, this is a for all statement. Now, you're going to prove this for all statement by the anonymous method. And then to prove what?
That P of L implies P of S of L.
Yes. Oops. And then you suppose then I'm just going to write ellipsis, right? Okay, you suppose then you have a to prove. Then you have a we compute. This to prove is closed of an as as required. The suppose is end concluded with a hence. The to prove with an as required. Then the anonymous method with a hence. And then the to prove with a as required. Now, here's the thing. Here is the other thing about this problem. When you're trying to do this, you can almost do this. Do this computation. But we're missing a rule. We're missing one step.
In hype.
Now, because I want to not spend time individually with each person with 1.5 hours, I'm going to tell you what the step that you're missing is. And that step is, this is a big homework spoiler. The following statements claim for all nats. I'm going to write it as in this way, N and M. The statement plus, let's say N S of M equals to plus S of N M. So this is a statement that you are allowed to move an S from the second argument to the first argument. And that's something that needs proof. So what happens is you go to the very start of this argument, and before everything, you write another claim and another proof of that statement. And then the proof of that claim is about as long as this claim. But once you have that claim, you give it a name. So maybe you can call this swap S. That would be a good name for the claim. And then you can use that to justify the last step of this we compute. And also, when you're doing the case Z, well, I mean, you have this right here. That looks like it's clearly related to the plus Z thing that we had in the notes that I just did above. So you are also going to need to cite that to finish the case plus Z. So your final argument is going to look like this. You're going to have claim, proof. Then this one is going to be in the notes. Let's call this Z on writes. Then you're going to have the statement and the proof of the swap as statement separately. And then you're going to have the statement and the proof of the main problem. And that is what a complete solution. Oh, but of course, we haven't closed everything off yet. Now you get to the very satisfying thing. So now you've closed off case S nat here. So that completes the case S nat. Now we go up above. What was the thing there? It was structural induction. So structural induction here, we close off structural induction with a hence for all m plus n m equals plus mn. And then the next thing was an anonymous method, so we close that off. I'll write it like this, n and m. Okay, you have a recording of this lecture. This is a guide for how to do PF1. And I want correct solutions from everyone. Any questions? We're going to take a break now and then start some new material.
I have a question.
Mhm.
Instead of showing plus n sm equals plus s n m, can I show that plus s n m equals s of plus n m?
Yeah, those two claims are related just by one step of computation, right?
Yeah. Uh-huh.
So yeah, they're
So it
basically the
would.
same. Yes, it would.
Okay.
You don't have to prove this claim. You can prove a similar claim. And anyway, you were supposed to discover that you were supposed to do this on your own.
Okay. Thank you.
And then homework 2 is similar. Actually, this claim is useful for homework 2 as well. But I want correct proof for both homework problems as well. So at the end of Friday's lecture, I really rushed going through the proof material, and I just left all of that in your notes. But looking at the submissions that I got, most people put a lot of effort into it. But I also thought that it would be very valuable to go through everything and explain it carefully so that I could get correct submissions. And hopefully, since I see that most of you put a bunch of work into it, what we did today was also useful in clarifying anything if you had any errors. Now you probably know if there are errors or not. Also, if you wrote any sort of proof constructs that were different from the proof constructs there, so you wrote like informal sentences, you wrote, we're going to show it has the same value, or other prose sentences, those aren't proof rules that we have available to us. So you can't write a prose argument. The proof structure that I have is so rigid that you can't sort of freely write anything. It always has to be some proof rule that you're applying. And what those proof rules are really it's a game. It's a game of proving things with these rules. You need to know the rules, and then you need to know what rules to play. But it's a game, in the same way that you can think of differentiating as a game, or that you can think of chess as a game. Although chess has an opponent, so I guess it's different. But if we imagine talking about playing chess against a specific AI, then yes, it's that. Although I guess you don't know what the AI is going to do, although you can look at the code. Anyway, so now we're taking a break. That was not new material. That was a proper explanation of what I rushed through on Friday that I needed to rush through in order to give you the assignment. So let's resume at 3:05. Let's actually do a bit later than 3:05. Let's do 3:07 with new material. Okay. See you then. Has anyone thought of questions?
Yeah, so like the rules that we have, like the plus z rule, are they themselves for all statements?
Oh, no, they are not. They can be, but in our case, we think of them as something lying outside of the language of logic. Well, rather, I'm going to explain how I think about rules in this section. So the answer to that question is if you really want them to, sure.
Okay, thanks.
Okay, actually, I can explain more concretely. Remember before when we were talking about like S-Kong, and we said, well, in S-Kong, the S and T were metavariables for any expression, right?
Yeah.
So you could substitute. Okay, yes. Roughly they're for all, but the variables are quantified over very specific domains. So for example, in S-Kong, you can say if S of Z goes to plus S of Z, which it doesn't, then S of Z goes to S of plus S of Z with S of Z. So this is a valid instance of this rule. I guess it's a for all. Basically, it's a for all. But this instance is sort of useless because the hypothetical is false. So you need to know what the for alls are quantified over. These are quantified over expressions, whereas for the other rules, they were quantified over nuts, right?
Right.
Now, here's why I don't like to say for all statements. Right now, in this universe of logic, we were only talking about for all statements quantified over nuts. But here now, we're talking about a for all statement quantified over expressions. So if you want to have for all statements over expressions, then you're allowed to do that. But at the moment, when we were doing that, we didn't have such statements, so we couldn't write for all expressions, right?
Right, could you say that you can't have that because expressions can't be counted? Or like they don't have an order to
If you don't have quantifiers over expressions, then your logic is not expressive enough to state the rule as a for all statement.
Got it. Okay, thank you.
That's a really that's the collection of words that express a correct answer. You'll know by the end of the class what that means, because at the end of the class, we'll see that logic is not absolute. There is no such thing as just being logical. If you tell someone in colloquial language that they should be logical, probably it has absolutely nothing to do with the laws of logic. They say very little about what people talk about in colloquial conversations. They say very little about life or about what you ought to do. And action, in a way, it's hard to say that someone's acting in a way is illogical. When you actually understand what logic is, logic has very little to do with life in a certain way. Or it does have things to do with life, but not in the way that people colloquially express it to or think it's to. And even then, logic is not absolute. There's no such thing as just logic. There are various different kinds of logic, and all of them have different flavors, and you can expand your logic with more proof rules, and then you can have logics that disagree on whether something is true or not. We'll see that in this course as well. So if you have a logic expressive enough to quantify overall expressions, then you can state the S-Kong rule as a for all rule. Okay. So this week, we are very quickly going to move on to very practical material. But we're going to start with a bit of a dose of theoretical things. And then at the end of the class, we're going to move on to practical things at the end of this lecture. So programming in Racket is very practical. The theoretical preamble about programming languages is less practical. Now, what you're really going to be surprised to discover is that last week we worked really hard. We only did it on Friday to define plus. We defined plus. And really, plus was sort of a program. Or a programming construct. What plus s of z meant was not only its value, but also the process used to get to that value. So the value would be s of z, and the process, which was this reduction plus s of z goes to s plus s of z goes to s of z. Yep. And that's basically how programming languages work. So you now know, you now understand the general way in which programming language constructs function. It was really hard to go to this definition. We spent all week in order to define plus. But the payoff is going to be apparent this week. Any questions? So I'm going to say one more thing about the universe of gnats in this lecture. But after this lecture, we are going to leave the universe of gnats behind. But we're going to temporarily leave it behind to talk about a completely different universe, in another universe. So this universe is called the universe of conditional expressions, or Bool. Bool and conditional expressions. And this is module 2 of the notes. Now, Booleans are a different sort of data type from gnats. Bools have a much simpler definition. A bool, I can define it by a grammar, is either true or false. There's no inductive recursive construction. It's just the grammar has two base cases, true and false. So true is a bool, false is a bool. And you really have no other rules for forming bools. So bools are simpler than gnats. Any questions? But what we want to form with bools is conditional expressions. And I'm just going to cut to the chase and show you what conditional expressions look like and how they behave. So here's an example. Well, the general conditional, okay, the simplest conditional expression looks like if true, false, true. So all conditional expressions that have an if consist of 3 different clauses inside of them. The first clause is the condition. The clause. This is the then clause. And this is the else clause. And you should think of a conditional expression as saying, if the first clause is true, then do the second thing. Otherwise, do the third thing. So conditional expressions are also going to have a notion of evaluation. And the evaluation of this, or rather the one-step reduction of this, which also evaluates it, is it looks at the condition, it's true. Since it's true, we're going with the then clause. So that becomes the second clause. Now, if that were all that we had, then this would be a much more boring universe than the universe of gnats. In fact, you'd only have so many expressions. You have 2 choices for what you can put for true, for the first position, the second position, and the third position. Then there would be 8 different things here, and then 2 other things here for false and true. But unlike pluses, where we didn't allow for nested pluses when we did last unit, we are going to allow for nested conditions. So in general, you could write statements like if, then, if, true, true, false, if, true, 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 false. So the grammar for what we're discussing is the grammar of conditional expressions. I'm going to, in this universe, I'm also going to call this EXPR. It is now a different universe, so the previous definition of a VXPR no longer applies. Okay, if I look at the 3 things that I encountered here, this guy, and this guy, what should the grammar for this universe be? What's is something that describes all of these together?
True, false.
Sorry, say that again. I didn't hear you.
So are we
ahead,
saying
anyone?
that true and false should count as an expression?
Yes, we are. So 2 variants of expression are true and false, and then what else is an expression?
If followed
Right.
by more expressions?
Yes, how many?
3?
Yep. So our universe now looks like this. The universe of conditional expressions an expression is either true, false, or if something, then something else something.
Excuse me.
Yes?
Instead of saying true, false, could we just make it 2 and say the first one is bool, and then if express.
Yes.
Instead of having
Yes,
two
we
separate.
can. So you can call both of these bool. So I can write that down as well. Bool, well, we had the definition above, is either true or false. And then we could replace both of these with bool. That would be another acceptable version of the grammar. The universe that they define of expressions is the same, right?
Yeah.
There's a reason that I'd prefer to write it like this, and we'll see why in a bit later. Actually, no. Oh, right. No, it would be fine. They're both equivalent. Yeah. So then how does if behave? I can define if by some rules. So first off, let's draw some ASTs for the things that we have here. If we look at this expression right here, this expression looks like if, and then I'm going to draw 3 children, true, false, true. And we're saying that whatever sort of evaluation we define on that, that should go to false. And in here, if we draw a tree for this tree would look like, well, there's an if at the top, then the left child is also an if, the leftmost one, true, false, true, true, false. If, true, true, true. And false. So that's what the AST for this expression above looks like. Remember, knots and the expressions in the universe of knots with pluses, the things that they generated were S expressions. If you just looked at the form of the grammar, you saw that no matter what strings they generated, those strings were S expressions. Similarly, in this grammar, the strings that they generate are also S expressions. True and false are valid node labels. And then the other constructor for expressions has a node label followed by 3 ASTs. So conditional expressions can also be seen as ASTs because conditional expressions as strings are S expressions. Any questions? Okay, so the rules. This is reduction rules or evaluation rules. So in AST form, let's say that T1 and T2 represents conditional expressions. So if you have if true, actually, let's write it like Okay, let's write it like this. If true, st. And then here, we're going to write if false, s and t. So here, I'm going to say s and t are meta variables for expressions. So in other words, s and t might be complicated trees with complicated conditional expressions in them. And what we find is that, well, what should the rules be? What should this tree reduce to?
S,
Yes. And the other one?
T.
Yep. So these two rules, I've written them in AST form, but I can give them names. And the names are if true and if false. And if I wanted to write them in S expression form, I would write if true st reduces to s, and if false, st reduces to t. Now, these two rules don't handle everything because the first thing doesn't necessarily have to be true or false. It can be any expression. And so what we need then, if we encountered this expression, we can't reduce it unless we know whether the value of the thing in the first position is true or false. And so if there's some computation left to do in the first position, in the conditional part of an if statement, then the computation should be directed to work there. And so that's a congruence rule. And the congruence rule might be stated as if, let's say in AST form, T1 goes to T1 prime. Let me write it like this. Actually, can anyone give me another letter apart from S and T that would be good for such expressions?
R.
Okay. If we use R's, then we can avoid talking about subscripts. So if R goes to R prime, then we're going to draw a tree that has if R, S, T. And that's the order that they're in the alphabet, isn't it? Good choice. Then this tree reduces to this tree. So that's how we state the congruence rule for if. So we can call that if cong. And then, of course, the statement in AST form would just be similar. If R goes to R prime, then if RST goes to, well, not goes to, reduces to, if R prime ST. So here are the three rules that govern the behavior of conditional expressions. I've given you a grammar for conditional expressions. A conditional expression is either, let's say it's the way that was suggested, it's either a bool or it's if expression. And a bool is either true or false. Now, we're going to define a notion of reduction on conditional expressions. Well, let's say my conditional expression is just true. Which rule here applies to true?
If true, right?
But there's no if. Let's say my conditional expression is just true.
Is that a conditional expression? If you
It
just
is.
have true?
It is, because look at the grammar. A conditional expression is either true, false, or if of three expressions.
Well, that's just the base case then, no? It would just be true.
Yes, and so what rules apply to true? What evaluation rules? How can I reduce true?
I think it's already reduced.
Good. So there are no rules that apply to true, and similarly, there are no rules that apply to false, right? Now, here's the cool part. Now, if your expression is not either true or false, then your expression has to be if of three things, right? Now, you look at the first thing in your if condition. That thing is either true, false, or similarly an if expression, right? So if it's true, then this is the rule that applies to it. If it's false, this is the thing that applies to it. And if it's neither true or false, then it's a conditional expression, which is in turn reducible. So the third rule applies to it. So we have a grammar for expressions. The three variants in the grammar are mutually exclusive. And we have three reduction rules so that if you have a bool, then no reduction rule applies to it. It's already reduced. But if you have a conditional expression that's not a bool, but that's an if statement, then exactly one of these three rules will apply to it, and we can determine the rule that will apply to it by looking at the form of the first arguments to the if. Just as with pluses, we could determine which rule applied to them based on the form of the second arguments which applied to them. Or more precisely, we could determine which rule applied to a comb based on whether it was S of a comb or whether it was just a plus. And if it was a plus, then the structure of the second argument of the plus would determine which rule was applicable. Any questions about that? So let's see what happens. So let's look at a calculation in AST form. By the way, for brevity, let's capital T denotes true and capital F denote false. So let's say we have if t if t f t f, then if let's make this an f, and then let's make this an if t f. So this is an AST representation of a conditional expression. Let's say I try and reduce it. Which reduction rule applies?
If congruence.
Yes. And then you look at the thing in the first argument, and then you try and reduce it. So what applies then?
If true.
Yeah. So you do a combination of if conc, and then on the inside, you apply the rule if true. And I'll write that explicitly. Okay, so what does this go to? What is in the condition case of the top level expression now?
If TFT.
Yep. And then what's the next rule that applies? Someone else.
If con,
Yep. And then what?
and then if true.
Good. And what does the left subtree reduce
question.
to? Yep.
How do you so in this case, right, like both, like there's two subtrees of length 2. How do you decide which one you evaluate first?
So look at what the rules say. What is global? So this is the point of the congruence rules. The point of the congruence rules are that they tell you where to direct computation. So computation starts originally at the top. What you're evaluating is this expression, right? Now, you look at this expression, you ask, how do I evaluate this expression? Well, which one of the 3 rules applies to it? It's the bottom one, right? Because the position on the left is not true, false, or it's not true or false. It's some compound expression. So then it says, well, look at the thing there and try and reduce it. So by applying if Kong, let's say at the first reduction, you started trying to compute this, and then it said, well, okay, see the thing in the first position and see where that would reduce to in one step, right? And then what rule applies here? It's the if t rule. No other rule applies here if this is the expression that you're trying to reduce. So for example, there's no congruence rule that would let you do a reduction in any position but the first position.
Oh, I see. I
Go ahead.
understand. Okay.
Oh, someone was about to ask a question. What else?
For second part, why don't we write if count twice?
Because you apply if conc,
Mhm.
then you're directing computation here. Now, what rule applies at this stage? Oh, yeah. So what rule applies at this stage right now? It's if true, right? Now, what about here? You apply if conc, you go to here, you're seeing what rule applies here. The rule that applies here is if true.
Oh, I see. Okay.
I can show you a situation in which you'd have two nested if concs next. It would be if you have if, and then if again in the first position. If here we had an if, then we'd have two nested if concs. Okay, okay, going back to this. So you applied the rule if conc and then if true. So what did the left subtree reduce to?
It would reduce to F.
Good. And then everything else is left as it was. And then here in the final, well, not the final, but what happens now? Someone who hasn't spoken with these answers?
If Kong, if true, it would evaluate the rightmost tree.
Wait, so you're saying that it would be if, but no, let's look at the statement of if Kong. If Kong says that if you have an if expression in which the first position can be reduced.
Oh, okay. Sorry, it's just if true.
So that's an important point. It's good that you ask the question then, because that clarifies that you can't do the computation elsewhere. You have to do the computation only where the rules say that you can do the computation. Right. So what's the rule then? The rule
just
is
if true.
Is it if true? Why would it be if true?
We're evaluating the rightmost tree, right?
Why are we evaluating the rightmost tree?
Because it can be reduced.
It can be reduced, but the top expression can't be reduced that way. You're not allowed to reduce any. So what we're trying to reduce, first off, what are we trying to reduce? We are trying to reduce not any subtree. What we're trying to reduce is the expression that we have globally. This expression globally. This is what we're trying to reduce, right?
Okay. Okay, so then since the first of the top expression is false, it would be if false.
Yes.
And then that becomes the third argument, which is itself another tree.
Yeah. And so that tree is, okay, well, I just write it. And then finally, we can take one more step. And what's the last step? Someone who hasn't spoken yet.
It will be true by the if true rule.
Good. So you apply the if true rule and you get down to true. So what is different about this universe of conditional expressions than the universe that we had before of plus and nuts? I mean, we encountered this difference a lot when we did this. What's the really big difference?
There's like 3 things, right?
Okay, that's one of them, but there's another one. Like the theoretical difference, there's a big qualitative theoretical thing that's changed. Think of if as something that's computation producing.
We only see a value, but nothing more complex, like the process.
Oh, so okay, what you're saying is that the values that we get at the end aren't like complicated inductive things that are either T or F. So it's easier in that way. The values are easier. Okay, that is true. But that's not what I was thinking of. Something else. Okay, so it's the thing that I clarified on Piazza, that for the assignment you weren't allowed to have nested pluses, right? If we think of the if or the plus as something that produces computation, in the universe with pluses, we only had a single plus in the expressions, or no pluses. Nats were also the expressions that we considered. Here, you have multiple expression-producing things, and there's a question of, well, which one, if they all produce computations, do I actually evaluate? So in the pluses, the congruence rule looked a bit superfluous, maybe, because you knew that on your next step, you just take the plus and you'd evaluate it, right? So what I mean, for example, is forgetting about any S congruence rules. If you have just S plus Z, S of Z, what's the next step? What do you do from this tree? Don't tell me the rules, just tell me what the resulting tree is. Anyone?
2 S's at the top.
Yep. And then plus. And then what? What are the children of plus?
It'll be ZZ.
Yep. So even if we ignore the if we ignore questions about S-Cong, you know that in these expressions that we encountered before, if there's a plus, it's the plus that's going to be doing the computing, right? This plus is actually going to, oh, sorry, I made a mistake. That should not be an S of Z. That should be S. I've written it as an S expression when I meant to write it as a AST. There we are. So the plus really caused the movements. It was the plus that made this movement happen. Similarly here, it was really this if that made the movement happen, but then in turn, this if directed it to here, and the actual computation, the actual reduction happened at this position. So the real computation here was that this thing fired. And the way that it fired is it caused a rewrite, and it caused this rewrite. Now, why was it this if that fired, and not, for example, this one on this step? And that's because the congruence rules directed the firing to a specific position. The firing always happens at the top position if it's possible to fire, given that there's a T or an F in this position. If there isn't a T or an F, then we don't know which one of these two trees to go to. We need to know whether this is true or false. So it says, okay, well, I can't fire, so I'm waiting for you to be done so that I can fire. So you fire. And then this, well, there's a true here. So this guy's happy to fire. And then it causes that computation. If there were another true here, then this in turn could not do its thing until this became a value. So the purpose of the if Kong rule here is really to direct computation. And in the universe of conditional expressions, there is a non-trivial amount of computation to direct to. We don't evaluate this tree at the start. We precisely don't. And the reason we don't is because that's what the if Kong rule says. The if Kong rule will not let us evaluate the last subtree until that subtree becomes the thing at the top, the topmost expression. Any questions about that?
Is it possible to just back up to the trees that we're just reducing to the last if condition, which triggered the if false?
Are you referring to a specific step, or are you saying something that we do from the first one?
No, a specific step.
Right?
Okay, so you have the tree that's circled in blue.
Yep.
So the reduction from there.
Right. So if we have an if thing, then the if thing, let's say this is supposed to fire. It looks at what's in its condition block. The thing in its condition block is actually a bool. It's not a complicated expression. It's either true or false. In this case, it's false. Now, the meaning then is that if it's false, this entire expression becomes the second thing. Whereas before, when we actually had trues, it became the first subtree. But because there's a false here, that directs the rule, which happens to be the if false rule, and that directs this entire tree to be rewritten as just this tree right here, which is the results. So it completely ignores this. In other words, if this thing were a complicated statement with ifs in it, that would never get evaluated. So let's put it this way. Let me give an example then below. Let's say you have if, and then you have true, and then you have true, and then you have if true, true, true. In this scenario, what happens is that we see that there are two ifs. And if we consider ifs as computation producing units, things that actually cause rewriting, then there are two things that can be rewritten. But the rules say that this one fires first. And when this one fires, it looks at what's in its condition position. It's true. And so the entire tree just gets rewritten to the thing in the first position, which is a true. Whoops, green. And so that second if is forgotten about. It never gets a chance to run. And in programming languages, imagine that you have something like successor case and base case, right? So here's a math statement. Think about factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And in general, we can define the factorial. We can define n factorial to be 1 if n is equal to 1, or 1 if n is equal to 0, And the factorial, n minus 1 factorial, times n, if n does not equal to 0. So what would happen then is if you try to calculate something like 3 factorial, you would see which one of these two rules applied. Well, is 3 equal to 0?
No.
So the second rule applies. And what happens is that 3 factorial gets rewritten as 3 times n minus 1 is 2 factorial, right?
Yeah.
Now you look at 2 factorial. And 2 is not 0 either. So you rewrite that as 3 times 2 times 1 factorial. Then 1 factorial isn't 0 either, so you write that as 3 times 2 times 1 times 0 factorial. And then finally, the 0 factorial becomes a 1. And then you get your answer. Now, here's the catch. Suppose that you evaluated both of these before you looked at the if condition. Then, instead of going with 1, you try and calculate minus 1 factorial, and then you'd calculate minus 2 factorial. And then that would go on, and you'd never finish the calculation. So if there's an if condition here, and you want it to happen that if n is equal to 0, you don't even try and evaluate this. Because otherwise, you're never going to be able to break out. You don't want to make a recursive call before checking the condition. That's a very high-level thing, and that doesn't mean something to us yet. But it's very important that this tree does not get evaluated. Because if this is some function, and what this unit of computation does is produce a recursive call, which it doesn't here, then this behavior of if precisely guarantees that you don't just infinitely make recursive calls instead of going to the base case. Or you don't make nonsense recursive calls is what would happen more frequently. Any more questions?
Okay, so, just to summarize, then in the latest example of the conditional the tree, since okay, so if goes to t, which is already reduced because it is t.
Yep.
So now the entire, so the whole thing reduces to t. So you don't
Yes,
look.
you
to
could
anything
also
else.
write
Okay.
that the whole thing evaluates to t.
Okay. Thank you.
And what rule applied here? What rule did we use here? Anyone?
If true.
Yep. Okay, so what we've done right now in the second part of the lecture so far is I've given you another universe. Before we were working in this universe of nats and pluses. Now, completely different page, completely different universe. It's the universe of Booleans and conditional expressions. Booleans are much simpler than nats. A bool is either true or false. And then a conditional expression, I can also write it, I can write it in the way that you said before. We could instead write, so I guess these are two different definitions that we can take. Instead, we could define EXPR is either bool or So two equivalent definitions. We can expand bool in the grammar, or we can leave it unexpanded. But okay, this way looks closer to what we had for pluses. Now a bool, by the computation that rules that we defined, is reduced. No computation rule applies to a bool. Whereas if you have some conditional expression, exactly one computation rule will apply to it. And that's the computation rule which will apply to it is precisely determined by the structure of the thing that you have in the first position. The thing that you have in the first position has to be some expression. Any expression is either a true, a false, or a conditional expression. And conditional expressions, I mean non-trivial ones, actual combs, ifs of some things, those are the things that still have some computation to do. So the third rule will apply. And so you'll always be able to make a step. Now, notice that when you actually do a computation, the complexity of the tree goes down. So let's say this tree had 4 nodes. It makes sense to count how many nodes there are in a tree, right? Does anyone not see what I mean by the idea of counting how many nodes there are in a tree?
Makes sense to me.
Right. So for example, let's look at this tree right here. How many nodes are there in it? Well, we can start counting, right? 1, 2.
13?
Let's see. Yep, 13. So there are 13 nodes in this tree. Now, we can actually tell right away how many. Oh, actually, so let's see what happened in this tree. In this tree, we got rid of 3 different nodes, right? We got rid of T, if, and F. So this tree would have 10 nodes. Now, in general, doing a step of computation doesn't always result in the number going down by 3. For example, in this case, this tree had 1, 2, 3, 4, 5, 6, 7 nodes. Whereas this tree only has 1 node. So if your computation throws out a big subtree, the number of nodes can go down by more than 2 or 3. By more than 3. But in any case, if you look at what the rule does, however many nodes T has, the number of nodes in this tree is the number of nodes that are in T plus 1 plus the number of nodes in S. So here, actually, so there are not 4 nodes. So I was false. I am very false. There are not 4 nodes here. This tree has how many nodes? This tree has 2 plus number of nodes in S. Nodes in S, let's say node size. Plus size T. You have this many nodes in this tree. Whereas in here, you only have size of S many nodes. Many nodes. So because the size of a tree, which is I define to be the number of nodes in a tree, is always 1 or more, we can't have empty trees. The grammar doesn't allow for empty. expressions, we see that the size goes down, and the size starts off as finite, and only a single rule applies at each step. And unless you're at a bool, then some rule is guaranteed to apply. Therefore, at each step, there is a unique step of computation, and there's this thing called the size of a tree, which goes down at every step. And it starts off as something finite, and it's always one or more. So therefore, this computation is eventually going to stop. And if it's at something to which no computation rules apply, then we know that that thing has to be a bool. So that defines an evaluation on trees, similar to how we defined the value of a plus expression before. So now we know how to evaluate trees. But it's not just an evaluation, it's a series of reduction steps that eventually get down to a value. So it's the same story as we had before, really. And we're going to see this over and over and over again. Okay, any more questions? Let's take a 5-minute break, and then I'm going to say one more thing after that. And then we're going to end for today. Actually, let's not do any more theoretical things today. Let's go on to some practical things. So 5-minute break, and then we're going to start fun practical things. So let's resume at 4:13. That's a good time, Homestuck time. Okay. Oh, does anyone have any questions now? I'm going to switch to this. Is the font size big enough for everyone to see? Oh, can people confirm that this is visible?
I just see Taras Kolomotsky has started screen sharing. That's all I see.
Ah,
Yes, same.
okay. Do you see it now?
No. Did you press share this screen or share this application?
Well, I have multiple desktops open, and oh, I see. There is a difference between desktop and application. Okay, this I'm now opening the desktop that has it. Do you see it now?
There we go.
Yes.
Okay, good. So this is Dr. Racket. It's the development environment for the Racket language. I sent you a link to the homepage where you can download this. Racket is very nice. The lecture notes, for example, are written in Racket, and the homework problems are graded. The actual grading scripts are also in Rackets. And then if you know the website Hacker News, run by Paul Graham of Y Combinator, that's also written in Rackets. So Hacker News application. That's probably one of the most famous ones. Now, Racket is a cool language. What I want to indicate is that Dr. Racket has many built-in languages. For example, when I'm doing the notes, I can do Scribble. There are some teaching languages. And the way that you can access those teaching languages is because you can go to the bottom of the page, and then you go to select language, and then you select a language. And the language that I want you to use right now is beginning student with list abbreviations. So that's the second one under the How to Design Programs tab. So I'm going to show you how to do that again. You go to the bottom, choose a language, choose the second language under How to Design Programs. And so I'll write that here. We'll start with beginning students plus list abbreviations. Now, so I've shown you how to write comments. If you have a semicolon at the start of a line, that'll be a comment. So none of this does anything. Now, Racket is a language that can be compiled, but usually you don't compile it. Usually, Racket runs in what is called a REPL, a read, evaluate, print loop. Which means that I can go to the bottom and I can type in some Racket expressions. So numbers are Racket expressions. Now, numbers are not our model of are not nats. Numbers are numbers in the proper sense. So you can type in something like 5, and Racket will evaluate 5. The value of 5 is 5. Similarly, you can type in something like true. And the value of true, well, Racket actually uses a different symbol. It's not true, it's hashtag true. Put that up on Instagram. So, but it recognizes the word true, but the value of true is hashtag true. And then you can do arithmetic. You can do something like 2 plus 2. And of course, the language is based on S expressions. So the plus would be a prefix operator. And that tells you 4. Now, as you can guess, in general, plus expressions, the expressions can be compound. So you can say times 2, 3. So that's 6. 6 plus 1. What do I get?
7.
What happens when I press enter?
7.
Yeah. So there are also strings, which you can worry about later, but the Hello Worlds program in Racket is as follows. It is a string, it is a value. That is Hello World. It is the value. It is literally that. There's no printing. There's no input output. There's no reading user inputs. It's just, this is a value. I've evaluated the string. It's the string. I've evaluated the arithmetic expression. It's the value of the arithmetic expression. Now, Booleans, you denote their values like this. So that's a value. There's nothing left to do. It's already evaluated, right? So Racket has expressions, has a universe of expressions. When you type 1 into the REPL, and this is the interactions window at the bottom, let's say the interactions window. Is bottom spelled with 2 T's? I'm not sure. It gets evaluated. And this is done via some rules, which we'll discuss later. So for example, we have that plus 2, well, this expression that we had before. So it gets evaluated in 0 or more steps to 7. So Racket has this universe of expressions, and then you can evaluate expressions. So that's a pretty familiar thing, right? What else what was the next thing? Okay, now plus is already something that's built in. So what are all of these things? Plus multiplication is done with an asterisk. Then you have subtraction and you have division are built-in operators. Racket evaluates them in a black box way. So they're just defined somehow. You have rules that somehow make sense of these applied to all sensible numbers. Now, notice, yes, there's probably is. I don't remember what the command, let's try exp. No, exp is exponential. So if we try exp1, it's going to give me 2.7172, isn't it? Yes, it is. It's going to give me the number e. This is e to the x. Let's try pow. Not defined.
Maybe it's a caret.
Oh, let's try that. Actually, that probably is a logical not operation. No, it's not.
Do you think that they have natural logarithms so that you could have exp 2 ln 2?
Yeah, so let's try log 1. Log 1 is probably going to, well, it's going to be 0 no matter what. Let's try log x1. Well, okay, that's going to be the identity. These are going to be inverses. And so if we try, yes, so log, that is the natural logarithm. You can also try like sine, sine 2. Oh, well, okay, this, let's see if it's in radians. We can try, how would I get something like pi in terms of inverse trigonometric functions?
So arcsine 1.
Arcsine 1.
Tennessee.
Oh, okay. There is an A. This is built in. I do not remember what it looks like. Maybe pi is built in. Is pi built in? Yes, it is. So let's try sine pi. It is in degrees. That is sacrilege. Okay, apparently Racket defaults to degrees.
You might just be trying to approximate 0. Badly.
It is. Thank you. Yes, it is approximating 0. That's e to the negative 16. That is a very small exponent. Okay, no, so it is in radians. This is approximately 0. But it's an inexact number. Oh, by the way, Racket supports arbitrary precision numbers. For other programming languages, sometimes you can have numbers overflow. So let's see if there's a factorial function built in. There isn't. Well, I'll show you how to define functions. You write define, and then you write the function name, and then you write what the parameters are. So for example, let's say you have, well, let's just do squared first. So I want to define the function x goes to x squared. Actually, here's another cool thing about Racket. In Racket, you can type in LaTeX commands. So for example, maps2. And then you can press Control \, and it'll switch it to the LaTeX character. So typing \maps2 and pressing CTRL plus \, it produces, and these are LaTeX commands. Encodings, LaTeX commands. Well, trivial ones that denote characters. Then you can do logic things, like you can do for all, and it'll actually go into that symbol. But what's even cooler is that Racket has a built-in shortcut for typing the letter lambda, which is a very special letter. Just CTRL, sorry, command on OS X, command plus \, gives a lambda. On Windows, these would be different. These are on OS X. Anyway, so let's consider the function x maps to x squared. So how would I define that? I'd say square, and then I'd say x, so that's the parameter. F of x is x squared. How do I write x squared?
Would you do times XX?
X times X, yeah.
Yep. So that's the definition. Now, so right now, if I look at the bottom and I type in square 2, what it'll tell me is that square is not defined. That's because these definitions have not yet been run. So I could, by the way, take this and I could define it in here. It doesn't let me do it in the definitions window. Okay, so beginning student language only lets you define things here. Okay, you've defined it here. In general Racket, you're allowed to do that in interactions window, but not in beginning student. You press run, and then it processes these definitions. So now it starts over again with this thing having been made sense of. Now I can type in square 2. Now that's something that's in my language, and this defines a rule. So defines, really, this lets me define a rule. A new evaluation rule. So in the same way that we had rules before, in this language, you can define as many rules as you want, just like this.
What would happen if you tried to do like square true?
Good. Whoops. So what's the error? Expects a number as a first argument, given true.
Maybe it's because multiplication expects a number, and we use multiplication definition.
Yep. Notice multiplication, colon,
that too.
multiplication expects a number as the first argument, given true. So in other words, Racket can tell the difference between numbers and Booleans, right? Now, so Racket has a universe of data. Some of these are nuts. Okay, then Racket also has values. Values in Rackets, and these are unreducible sensical expressions. These are, okay, so Racket has a definition of values. Values are, for example, numbers, Booleans, and several other things, which we'll discuss later. Now, in the universe of expressions, some expressions are values. And those values, Racket can tell which one is which. And the word that I'm going to use here is type, the type of a value. And how would I do that? Well, I can, let's say, type in the word number, and I can put a question mark after it. And I can say, is true a number? And what will Racket say?
False.
Hashtag false. Yep. So the value for true and false is the hashtag. And you can say, it's not bool, but it's the full word, Boolean. Boolean 1. False. Is 1 a number? True. So in other words, Racket will, if you try and multiply two things which are not numbers, Racket will tell you that there's an issue. And so in a way, if you look at an expression like this and you plug in some value, you can tell whether there's an issue or not based on whether the argument satisfies this predicate. So this thing that lets you test whether something is or not something is called a predicate. Well, a predicate is anything that consumes one argument and produces a Boolean. So have predicates like number and Boolean for classifying values. Okay, what does anyone want to try something now? I'm sure there are some suggestions.
Do you think we could define nats in the S syntax we've expressed them as before?
We can. That requires structures. So, okay, I can show you how to do that. Define structs. So I think that I do this. Define struct S, sorry, Z. Let's see if it's going to let me do that. Okay, notice. Okay, so I'm defining a structure. It's called Z, and it has nothing, no children. As an AST, Z has no children. So here's the problem. Here is, I said that Racket is a language based on S expressions. That's sort of false because you're allowed to do this. If you have a structure that has no children, then you make an instance of that structure by enclosing Z in parentheses. Sorry, you say make struct. Oh, very good. Never mind. Make struct. You're not allowed in beginning student language. You're not allowed to do that. So you say make struct Z. Sorry, make Z. And make Z takes no arguments. So here's where it breaks the AST language. There are no children to specify. By the way, what happens? Someone should ask a very pressing question right now. Can anyone figure it out? What happens if I just type in make Z without the brackets?
Oh, yeah.
So what happens if I have 1, right? 1, the value is 1. What's the value of open paren, close paren 1? What should I get?
Well, if it's parentheses, does that mean that we're expecting a function?
Yep.
So, yeah.
So no. In other words, what we learned is in Rackets, every parenthesis is essential. No more, no less. Or else you get errors. Unintended behavior. Okay, then we can define structs. And we can call this struct S. And S is going to take some arguments. Let's call that N, lowercase n. Then I can, for example, say make. So in beginning Rackets, you have to type make S instead of just S. Make S, make Z. And the value is that. That is S of Z. The make is part of the value. Now we want to define addition, right? Of course. Oh, now this here has been printed as output. What that means is that this is a value. And as a value, Racket has ways of classifying values. So you can probably type S question mark. This. And it'll say true. So when you say this, it introduces a way to tell whether something is a successor or not. And there's also should be a way to access the thing inside of it. So you can say S hyphen N, this, and that accesses the thing inside of the S. So what should that give me?
Would it be make Z?
Good. So given that we have predicates, ways to check whether something is an S or a Z, and a way to access positions, and a way to define functions, we can now try and define that. Define plus, let's call the two arguments, let's call them X and Y, because I use N here. Actually, let's, what's a better thing to use than a nats? Let's say successor, let's call this nats. No, that's a bad name. Successor val. So let's define plus nm. Now, by the way, Racket also has if conditions. If true, true, false. What do I get if I spell that correctly? What should the value of this be?
True.
Hashtag true.
Yeah.
Okay, so given that I can do this, define plus nm, how should I define addition? Of nuts. So let's recall the definition. We want plus of n and then make s or make z. We want that to reduce to n, right? And we want plus n make s of what? Of anything. Of some k to reduce to make, reduce to what? Make s of what?
Plus nk.
Right. Now, we don't have k, but we can access k from inside M by using the predicates and the accessor, right? So how should I define plus? So I can start with an if, right? To tell which one of these two cases it is. How do I tell if it's the first case?
If parentheses make Z, I mean, no, Z question mark
Yep.
of, was it M?
Then what?
Then plus NM reduces to N.
So what do I get? What's the result? Just
You get N.
okay. And
Yeah.
in the other case?
S question mark.
Well, we know that it's not Z. So we can assume
just
that
else then. Right.
Yes. Well, there's no else. It's just first, second, third. First expression, second expression, third expression. So what's the third expression?
Oh, it'd be well, we didn't say if how many S's M has. So
Look at this.
I mean, yeah, I mean, we could say it's like just make S plus N K, but do we have to define K so that
What is K?
is,
What is K though? How do I get K?
yeah, I guess we have to set K equals make S val, right? That's how we defined.
So K would be if this is past a argument that is either make S or make Z or make S, then if it's not Z, we can assume that it's a make S.
Okay, yeah.
And then if it's a make S, then how can I access the thing inside of the make S? Well, I changed my name.
Right?
Yeah, but I
SN
changed
function.
S. I renamed N to val, right?
Oh, okay, yeah, that's what that function did.
Of
make S K. What? Yeah.
well, I want to recognize M as make SK, right?
Yeah.
Well, there is no K yet. There's only M.
Okay. Sorry. S val M, right?
Yeah. So that's what's inside of the M. By the way, everyone's doing a very good job so far. I've just completely introduced a new thing and we are just going on the fly and doing it. So plus N, S val M. So that accesses the thing on the inside. That closes that make S. That closes that if. That closes that define. And notice in Racket, Dr. Racket will highlight. They'll match the parentheses. And it'll highlight the thing in the middle. So matching parentheses is supposed to be something that's made as easy as possible in this language because there are a lot of parentheses. So let's try that. So it looks like we have a definition of plus.
I have a question.
And so, yeah.
Is indentation important to Racket?
It's not. It's not. It would be much worse if it was. One line. It's less readable, but you can do it in one line.
Okay.
Okay, so if what is 1 plus 1? How do I how do I put S of Z in Racket in this language? What do I type to get S of Z?
Make dash S of make dash Z.
Good. And let's do 1 plus 1. And what's the result? Make S, make S, make Z. Now, this definition right here, I removed all the spacing. Really, I would be much less happy with this language if indentation mattered. It doesn't. In fact, but I've chose to indent it like this. Well, it's if I press enter, it automatically indents to what level it sees fits for the next line. Oh, and before we had, for example, factorial function. For numbers, we can define factorial. This is going to be for numbers now, not for nats. As what? If now numbers, 0 is a special number. So I can ask if 0, n. And I can say 1. Otherwise, I can say multiplication of n with facts. So I can write recursive functions. And then I can type in n minus 1. There's a shortcut for that, sub 1 n. So I can also do that. And the reason that I was before talking about factorials, so this is the last thing for today, This is another really cool thing about Racket. So you can say fact 5. So factorial is a function that grows really quickly. Now, on most programming languages, you have like 32 or 64-bit numbers. And if a number becomes very big, it eventually wraps around. In Racket, you have unlimited size numbers. So I can say fact is really grows quickly. Let's do fact 20. Okay, that's not that big. Let's do fact 30. Okay, that's still pretty small. That's a bit longer. Let's do fact 300. Unlimited size numbers. So this is the language that we're going to be working with this term. And again, it's a really fun language. There are expressions. It evaluates expressions. The hello world program is just literally the hello world. It's a string. The strings are values. There, we've evaluated hello world. No input output, no file IO. REPL, you don't have to compile things. You just define things, you run them, and then you run anything you want here. So today I have not yet defined what all of these things are. Today was just a tour of some of the features that you have. So I haven't actually explained anything in here. Now, I want to have a very easy homework assignment. Do maybe tomorrow, I'll make it due on Wednesday. It's going to be an assignment that's going to take 10 minutes or 15 minutes tops. Just about writing arithmetic expressions in prefix notation. And about writing some way to do a trace. Oh, by the way, you can type in expressions in this window as well. If you type in expressions, they get, when you press run, evaluated. So any expressions that you have here get it evaluated. And you can type in more. You can type in 2, 1, 1. And then there are going to be 4 expressions that need evaluation. And those are the values of those expressions. And then the definitions stay here. But I'll explain the assignment by email. It's just going to be basically write down a few computational traces and convert a math expression into prefix notation. Any questions? How do people like this language?
Should be
Different.
Oh, and by the way, there are no variables that you can change. You can't set a value and then change it in this language. Full Racket supports mutation, but it's considered impure, and the student languages don't even let you do impure operations like this. There are no loops either. Recursion only. And this is a really good IDE to use. And it makes it very easy to match parents. Okay, so that's all for today. Have a nice day. See you on Wednesday, right? Wednesday and Thursday.
You too.
Wednesday. Bye.
Wednesday.
Yeah.